In 2009, Dan Hooper and his colleagues found a glow coming from the center of our that no one had ever noticed before. After analyzing publicly available data from the Fermi Gamma Ray Space Telescope, a satellite launched a year earlier, the team concluded that the center of the Milky Way was radiating more gamma rays than astrophysicists could account for. The finding was so unexpected that, at the time, few believed that it was real. It didn't help that Hooper wasn't a member of the Fermi collaboration, but rather an outsider picking over the data that the Fermi team made public. One of the scientists working on Fermi called his work amateurish, arguing that Hooper simply didn't know how to properly interpret the data. Yet as time wore on, astrophysicists began to realize that there's a lot more high-energy radiationing through than they could explain. Just a year before Hooper started analyzing Fermi data, a gamma ray detector in New Mexico called Milagro had found an abundance of super-energetic gamma rays that appeared to come from all across the galactic plane. And in 2014, the Alpha Magnetic Spectrometer AMS, an experiment on the International Space Station, found more antimatter ring through than could be accounted for, confirming earlier observations by satellite and balloon experiments. These three anomalies, if real, showed that something was going on in the universe that we didn't know about. A number of astrophysicists, including Hooper, began to argue that two of these mysterious signals were an astrophysical echo of dark matter, the profoundly mysterious substance thought to make up about a quarter of the universe. This year, almost a decade after the launch of the Fermi telescope, researchers have nearly arrived at a consensus. First, pretty much all astrophysicists now agree that the center of our Milky Way produces much more gamma radiation than our models of known gamma ray sources suggest, said Luigi Tebaldo, an astrophysicist at Stanford University and member of the Fermi collaboration, thus validating Hooper's once amateurish claims. Second, all that extra radiation is probably not due to dark matter. A number of recent studies have convinced many researchers that pulsars, rapidly spinning neutron stars, can explain all three mysteries. The only problem is that no one seems to be able to find them. Dark matter days the center of the is a crowded place, dense with stars, dust and, presumably, dark matter. Astrophysicists have long believed that dark matter is probably made out of particles that don't readily interact with ordinary matter, so-called weakly interacting massive particles, or WIMPs. Occasionally these WIMPs might collide with one another. When they do, they could produce gamma rays. Perhaps that's just what's going on in the galactic center, Hooper suggested back in 2009. The theory dovetailed with another idea that Hooper had put forward just a year earlier. In 2008, he and three co-authors published a paper arguing that collisions of neutralinos, a type of WIMP, generated showers of exotic particles that then decayed into elementary particles. The process would explain the anomalously high levels of positrons, the antimatter counterpart of electrons found earlier by a space-based experiment called Pamela. In this case, Hooper was in good company. Since Pamela's first results, without exaggeration, around 1,000 papers have tried to explain the positron excess mystery, said Tim Linden, an astrophysicist at Ohio State University. The majority of these papers favored the dark matter interpretation. In 2014, the Pamela results were buttressed by data coming from the AMS. Yet other scientists quickly started to poke holes in both of these dark matter-based explanations. In the case of the galactic center, WIMP collisions should create a smooth, hazy glow of gamma rays, like a floodlight seen through thick fog. When astrophysicists examined the gamma ray glow in detail, however, they found a pointless patchwork of light. It appeared as though the gamma rays were coming from many individual point sources. And if WIMPs were producing all those positrons, they should also be creating a lot of gamma rays. Yet when astronomers look out at nearby dwarf galaxies, thought to be home to a huge amount of dark matter, the gamma rays don't appear. The tension in these dark matter models has forced astrophysicists to consider some more astrophysically prosaic options. The rise of pulsars. Even though most scientists are fairly certain that dark matter exists even if we cannot directly observe it, the models are still considered exotic. What's much less exotic are astrophysical sources of radiation that we can actually detect with our telescopes. So as the data began to undermine the case for dark matter, many researchers, including Hooper, began to contemplate a much more mundane explanation: pulsars. Pulsars are ultra-dense, rapidly rotating objects, neutron stars, the dead cores of massive stars that have gone supernova. They emit jets of radiation that spin around with a pulsar like the beam from a lighthouse. As this beam crosses Earth, our telescopes register a flash of energy. In 2015, two groups, one led by Christoph Weniger, an astrophysicist at the University of Amsterdam, and the other by Tracy Slatcher, a theoretical physicist at the Massachusetts Institute of Technology, separately presented evidence that gave the pulsar theory a major boost. Each team used slightly different methods, but essentially they both divided the region of the sky covering the galactic center into numerous pixels. They then counted the number of fluctuations in each pixel, watching, essentially, for lighthouse beams to swing across the face of Earth. The researchers discovered big differences between pixels, hot and cold patches in the sky, which are much easier to explain if one assumes that the signal comes from different point sources. This is what you would expect from pulsars, because there could be brighter pulsars, or more pulsars, at some sky locations compared to others, said Linden. Most astrophysicists now think that the strange abundance of positrons in them may also be due to pulsars. Pulsars generate huge magnetic fields that spin along with the rest of the object. A spinning magnetic field will generate an electric field, and this electric field pulls electrons from the surface of the pulsar and accelerates them rapidly. As the electrons curve through the magnetic fields, the electrons will emit high-energy gamma rays. Some of this radiation is energetic enough to spontaneously morph into pairs of electrons and positrons that then escape from the pulsar's strong magnetic grasp. There are a lot of steps in this process, and a lot of uncertainty. Specifically, researchers want to know how much of the pulsar's energy goes into making these electron-positron pairs. Is it a fraction of a percentage point? Or a significant total, something like 20 or even 40% of the pulsar's energy? If the latter, pulsars might be making enough positrons to explain the antimatter excess. Researchers had to find a way to measure the number of electrons and positrons coming out of pulsars. Unfortunately, this is an extremely difficult task. Electrons and positrons, being charged particles, will loop and twist their way through the. If you detect one from Earth, it's hard to know where it came from. Gamma rays, on the other hand, stick to a straight path. With this in mind, researchers working with the High-Altitude Water Cherenkov Gamma Ray Observatory HAWC in Mexico have recently made detailed studies of two relatively bright and relatively nearby pulsars, Gemma and Monogem. They examined not just the gamma rays coming from the pulsar itself but also the super-energetic gamma rays 1,000 times more energetic than the accessing from the galactic center that appeared as a relatively broad halo around the pulsars. Throughout this halo, high-energy electrons coming from the pulsar collided with low-energy photons from ambient starlight. The collisions transferred huge amounts of energy to the pokey photons, like a sledgehammer smashing golf balls into orbit. Earlier this year, a team that included Hooper and Linden published a study that compared the brightness of the pulsars with the brightness of their halos. They concluded that 8 to 27% of Gemma's energy had to be converted to electrons and positrons, said Linden. For Monogem, it was twice as much. This means that pulsars produce a tremendous population of electrons and positrons within hour, said Linden. Slatcher said the research is the first time we've really had any handle on the spectrum of high-energy positrons produced by pulsars, so this is a big step forward. The work also helps to explain the strange excess of very high-energy gamma rays that were found a decade ago by the Milagro detector in New Mexico. The radiation could be coming from pulsar-generated electrons and positrons accelerating ambient starlight. Dark matter's revenge. One hurdle remains finding enough pulsars to account for all the mysterious emission. We should see about 50 bright pulsars in the galactic center to produce the excess, said Linden. Instead we've only found a handful. Similarly, we don't yet know of enough pulsars in the rest of the to explain away the positron excess or the abundance of ultra-high-energy gamma rays found by Milagro and HAWC. The issue doesn't bother pulsar proponents that much though. They hope that in the near future a new generation of radio telescopes, such as Meerkat in South Africa and its planned successor, the Square Kilometre Array in South Africa and Australia, will find the so far invisible radio sources in our. So is the dark matters, pulsars debate settled. For positrons, it appears to be so. While many more researchers used to favor the dark matter interpretation originally, most now lean towards pulsars. And in the galactic center, pulsars are the Occam's razor candidate, said Slatcher. You could explain the data just as well with a dark matter annihilation scenario, but we knew pulsars were there and we don't know if dark matter annihilates, so you could consider the pulsar scenario to be simpler. According to Slatya, the dark matter explanation for the galactic center could yet make a comeback, and there is indeed another way to test the dark matter hypothesis. When cosmic rays interact with interstellar material, and, in theory, during dark matter annihilations, they produce antiprotons, the antiparticle twin of a proton. Pulsars cannot produce antiprotons. If researchers were to find more antiprotons than could be accounted for by cosmic rays, the discovery would boost the dark matter scenario. This is exactly what preliminary results from AMS have shown, a possible excess of antiprotons that may be consistent with annihilating dark matter particles. AMS scientists aren't making any conclusions about the source of the antiprotons, but 2 papers came out this year arguing that dark matter could be behind the antiproton excess. For Linden, the pulsar confirmation would mean even more. For decades, he said, when we have thought about the energetics of cosmic rays in our universe, we've always thought about supernovas, producing protons that then generate all of the cosmic rays detected. We have had this really pretty picture where supernovas produce everything, said Linden. Everything links together and looks perfect. But in setting up that model, the energetics from pulsars are generally neglected, he added, despite pulsars being among the highest energy objects in space. So if this new picture holds up, and pulsars produce these excesses, then it really changes our interpretation of the source of most of the very energetic radiation in galaxies, and maybe throughout the universe, said Linden. It might be a case of pulsars 3, dark matter 0, at least for now. But I would be lying if I said I didn't want these signals to turn out to be dark matter, said Linden. That would be so much more exciting. This article was reprinted on Wired.com.